Okay, a very useful example. Actually, let's do an exercise. I want you to pause the video and think about this. You're going to have to go back to the definition of a sequence of partial sums. And also the definition of a convergent series. And the test for divergence. You're going to need all three of these things to answer this question. So the answer is, well, I got a weird notation here. Okay, well, this just means, summation n equals 1 to infinity, of course. It's just written in a different way. Okay, A. So limit of Sn is 3 over 2. So what does this tell me? It tells me that Sn is convergent, and therefore summation An is convergent. By definition. Okay, by definition of a convergent series. Okay, so what's next? How about red? Limit of An not equal to 0. That would imply that summation An diverges, right? But what if I negate both sides? So logically, if you reverse or take the logical opposite of both sides, okay, what happens? Well, the arrow changes direction. This is test for divergence. So if I reverse test for divergence, then I'm allowed to conclude that if the summation of An converges, then the limit of An must be 0. So from here, I conclude that limit of An must be 0. That was part A. Part B is easier. Lim n goes to infinity. Summation. What is it? I equals 1. I equals 1 to n of An. And okay, what is this? Well, this is just, this is exactly Sn. Okay, that's the nth partial sum. And we're told earlier the limit of that is 3 over 2. Okay, this is the nth partial sum. Okay, more details on that. Summation I equals 1 up to n e of An. That is the sum that starts at A1 and stops. Stops at An. Okay, what do we mean when we write that down? That's exactly Sn.